All right, everyone, welcome back. So here we're going to talk about current and voltage in conductors. So we will investigate and verify Ohm's law. Ohm's law, if you remember, shows or represents how the some of the circuit quantities like voltage, current, and resistance related to one another. So the important thing about Ohm's law, it shows how the current is proportional to voltage, and also how current is proportional to 1 over resistance. That means voltage is sort of like a driving force. Well, it's not a force, but let's say driving mechanism to push those charges. And the flow of charges is what we define to be the current. But then the resistance is something that technically can use to control the current flow. That means, the voltage allows us to create electric field in the circuit and have the charges move around. Resistance, on the other hand, resists basically in terms of it allows the material to resist the flow of charges. And higher the resistance of the material, as we learned, right, the lower the current in the circuit. All right, so we're going to have a relatively straightforward experimental setup. So we're going to have a battery. So let's say here's the symbol for the battery. And then we're going to have a different resistors in the circuit. So here's how we represent the resistor. This is the symbol for the resistor. And then let's say what I have here is, I have here is point A, which will then be connected to the positive terminal of the battery. And then on the other side, then there's a point B, which will be connected then to the negative side of the battery. Like that. Let me do maybe a little better. There you go. So then R represents the resistance of the resistor. Now, in order for us to investigate this Ohm's law, which is basically in terms of the voltage equals current times resistance, we're pretty much looking at this equation. We want to see how, if we have a resistor, if we have a resistor that the value of resistance is unknown to us, we can find the resistance by using this equation. Because one of the things we have here is then this delta V, which is the potential difference between the plates or the terminals of the battery, end up being the same as the potential difference between points A and B, because we have just one single resistor and it's connected to the, to the battery. Now, what we can do here is this. We can use multimeters to measure the current in the circuit and let's say the voltage. For example, let's say the voltage is, let's say 1 volt. Okay. So if the voltage, which is the potential difference between terminals of the battery, is 1 volt, that means if I connect a voltmeter, so here's a symbol for the voltmeter, across the resistor that points A and B, then this voltmeter will also measure 1 volt. Okay, so it should then give me the potential difference between the resistor, in terms of between points A and B, which give me potential difference across the resistor. And this is how we always measure the voltage of a device. We always connect between, or between 2 points, right, or across the device that we want, and then the voltmeter, gives us the voltage or the potential difference between those 2 points, between points A and B. All right, so that means what I can do here is use the voltmeter to measure the voltage across the resistor. Then I can use ammeter, which is a device that measures the current. It's connected sort of like, let's say, between the battery and the resistor. So hook up an ammeter like this, and then this will measure the current going through the resistor. Because ammeter is in series with the resistor, it will then measure the same current. Remember, two devices that are in series, they're always going to have the same current because there's pretty much, one path for the current. So the current is going to come like this and then continue like that, go through the ammeter, and then come back to the negative terminal. Okay. Now, that means the current goes around in the circuit, and it also goes through the ammeter, and ammeter records the value. That means when the potential difference across the resistor is same as the voltage of the battery in terms of, like, let's say here's 1 volt, I can measure what's the current in the circuit. But then what I can do here is, if I change this to 2 volts, then the the voltage here will voltmeter, right, will also measure that as 2 volts. Current then will also change. Then what we want to know here is this: if we continue increasing the voltage in the battery, what will happen to the current? Is it going to increase? Is it going to decrease? Well, according to the equation, right, current and voltage are directly proportional. That means if I continue increasing the voltage, the current should increase. And according to the Ohm's law, it's a linear relationship. It's a direct linear relationship. That means what we're going to do here is we're going to take a data where I'm going to say, all right, so this is going to be my voltage in volts, and let's say this is my current in amps, and I'm going to measure the voltage 1, current 1, voltage 2, current 2, voltage 3, current 3, and let's say dot dot dot. That means measure the voltage change and the current according to that current change, and use that to plot and find the relationship. That means using this equation, I can see that if I make a graph where the y-axis is the voltage in volts, and then the x-axis is the current in amps, if according to the Ohm's law they are directly proportional, they should be directly proportional, my graph should be something like that. So this is known as an ohmic, let's say, resistor or ohmic system. That means whenever my circuit behaves like where the voltage is increasing and then the current increasing proportional to the voltage increase, and then the plot of voltage versus current gives me a graph like that, that means the resistor that I have in the circuit is allowing me to have this direct linear relationship. That means that resistor is known as an ohmic resistor. Okay. That means ohmic resistor are the ones that allow voltage and current to be linearly proportional like this. Okay. Not every resistor technically can be ohmic, which means that some, let's say, some graphs can be not necessarily linear, something like this. So you might see some graph like that sometimes. Those are examples. If you do voltage versus current, so you get something like that. Obviously then that's type of resistor that gives me that voltage current relationship is not ohmic. And what we're going to do in this lab, we're going to have 4 different resistors, 4 different devices that act like a resistor, and we're going to see which one of them is ohmic, which one of them is not. That means when you have the resistor connected to the battery and you measure the voltage across and then current through the resistor, and then take the voltage versus current data and then plot them, this graph should tell you if the resistor is ohmic or not. All right, that means it's relatively straightforward in a way that the circuit, as I say, right, is very simple. So it's a simple circuit. We have resistor, voltmeter, ammeter, and a battery. Basically, we have just 4 circuit elements in our circuit, and we're gonna then take voltage versus current measurement, which you'll see is every time then we increase, right, dial the voltage, the current will also increase, and we just need to like record that. We just need to record that. Also, according to this equation, voltage equals resistance times current, right? If I write it like that, I can see that if I'm plotting this and getting the linear relationship like this, then y, I'm basically using this equation, right? Y equals then the slope times then the, whatever I have an x-axis. If I'm using the voltage on the y-axis and the current on the x-axis, then I can see that whatever the slope I get for this graph is directly equals to my resistor, okay? Because if I do, let's say if I find 2 points on this line, this is going to be then, my voltage, and this is going to be my current, and voltage over current, which is rise over run, is basically my resistor. Like obviously that's not what we want to do, right? We don't want to like just let's say use 1 or 2 points because the pivot interactives allows us to do the graph, and it allows us to find the correct fit, and we'll get then the slope directly from the graph, from the software. And that means that's what we're going to do. So we're going to find the correct fit, then find the slope, and then the slope value will give us then the resistance. Okay, resistance of that resistor. All right, so then the goal for today's lab is to connect 4 different devices which act like a resistor to our battery, measure the voltage and current, as a function of time. That means, voltage, let's say, 5 to 10 measurements of voltage, and every time then the voltage changes, measure how the current changes, and then plot it and use the slope to get the resistor, and you use the type of graph you get to figure out if it's ohmic or not. That means the theory itself is relatively straightforward. So we're just investigating Ohm's law. Now let's go then look at the experiment itself. All right, so this is our lab, current and voltage in conductors. We can write the learning objectives to find the relationship between the electric potential difference across a device and the current through the device, to see how this relationship varies for different types of devices that are used in electric circuits. And I pretty much give you the theory, the one that I just talked about, so you can read on that as well, and then see which one of this following graph correctly represents Ohm's law. So hopefully if you followed my lecture, you're able to answer the questions here. By the way, one of the things you should um, pay attention to in terms of how many submissions you actually allowed to have. See, this is 2 out of 2 submissions remaining. That means, you get 2 submissions. You try once, you get it wrong, we'll try it again. That means you get 2 submissions, make sure to use them. All right, so then let's look at, the experiment. So you can see, right, what I have here is there's, current and voltage interactive, which is where our experiment is. So you have the circuit that I drew, pretty much, you should be able to recognize it here. This is my resistor. This is the battery, right? So the positive terminal and negative terminal. So think like this. If I would draw this, a circuit diagram for this, this is my resistor like this. So then this is point, let's say point B, and this is point A. Okay. Now you can see, right, there's a voltmeter connected to the point A and B. So this is my voltmeter. And then point B is connected to the negative terminal. Point A is connected to the positive terminal. We just put an ammeter in between. Voltmeter measures in volts, ammeter measures in milliamps. So you have to be careful because we want to have a voltage versus current in amps. Voltage in volts, current in amps. So this is in milliamps, so make sure you do the conversion correctly. All right. So we're also given that there's a device that has 120 ohm, resistance. In a way, you given the resistance value, so you can then verify that by looking at the slope of the graph. Okay. So what we get then from here is this. Our experiment, so you can say, right, you can have a resistor, 120 ohm resistor, then electric motor, cooling fan, incandescent filament light bulb, and spool of wire. So you have 4 different devices. So you're going to do the same experiment for all 4 devices and see which one is ohmic, which one is not. That means verifying the Ohm's law. Okay. So let's start with this. In terms of then experiment, let's watch it quickly. By the way, I want to show that what we do here, we start with 0 voltage in the circuit. So you can see, right, voltmeter reads 0, well, the current is 0. And as soon as we start increasing the voltage, because one thing we can do, we can increase the voltage, even though some power supplies allow us to also increase the current. That means you can increase current and see how the voltage changes, or increase voltage and see how the current changes. Doesn't really matter. So let's say we start increasing the voltage. As you can see, right, as we start increasing the voltage, current starts increasing as well. And then you can see, right, we increase voltage until, let's say, we get all the way to 10 volts, and we pretty much stop the experiment. All right, so your your experimental measurements will be looking at the voltage at some instant of time, and then measure the current. Now we can see that we go from 0 to 10. Probably good idea then to have 10 measurements, where each measurement will be in terms of 1 volt increment. That means when the voltage is 0, what is the current? When voltage is 1, what is the current? When voltage is 2, what is the current? And so on. That gives you basically 10 measurements. All right. So here it says understanding the circuits. So these are some questions that I want you guys to um, answer. And again, look at the number of submissions you have. The goal for me is for you to learn. You get it wrong, well, try again until you get it right, and try to understand why you got it wrong in the first place. And when you finally get it right, hopefully you learn from your mistakes, right? So why you got it wrong, and why right now what you have is the correct answer. All right, so let's look at the trial one, which is the 120 ohm resistor. You can see, right? So you have a table, voltage versus current, and then you're gonna do the graph. So for example, um, if you do the 120 ohm resistor, see, you start with 0 0. That means you're gonna come back here and say, all right, so my measurement here is 0, and then this is 0. Okay. Then you can see, right, you voltage going to change. So what you want to do here is pretty much come back and say, all right, so I'm going to look at it in terms of increments of 1 volt. So when this is 1, 2, 3, 4, here just hit enter. You can do the next one, hit enter, then 6, and so on and so forth. So I'll do a few measurements so you guys can see. So let's say when voltage is 1 volt, what would we get? So, all right, so this is basically voltage as 1 volt. All right, because you can even zoom in and see, right? So that's basically 1 volt exactly. So then what is the current? Well, the current here is in milliamps. So what I can see here is, so this is 5, 10, 15, 20. So each mark is basically increments of 5 milliamps. So I would say that this is about 8 milliamps. All right, 8 milliamps. Well, milli stands for 1,000, right? So that means, 8 milliamps will be, 8 divided by 1,000. So 0.008. Okay, so this is my first measurement. And then you go into when the voltage here is 2. Okay, roughly that. And then you can see, right, it's all, almost, 20 milliamps. So I would say mostly, probably more accurately, it will be like 19 milliamps. Okay, so I go back and I write down here is 0.0019. So this is 0.019. That's 19 milliamps. And then one last measurement. So let's say when it's 3. All right. So then I get roughly 30. No, this is 27. Probably about 27 or 28 milliamps. So 0.028. All right. So then, all right. So then we take that data that we have. So we plot voltage on the y-axis, current on the x-axis, and we get our data set. Remember, so you need up to 10 data points. So then you want to see, is this linear or not? So that means you want to look at in terms of linear or proportional, right? So since we start from 0 0, then you can pretty much go in terms of proportional. You do this line, and then you can see, right, it's fairly proportional. Remember that it was 120 volts, 120 ohms for the resistance. If you scroll down, you look at the resistance that we got, which is the slope of this line. So I got 108. So not that close, but remember, I didn't take enough data points. So maybe if you get all 10 or more data points, right, you can get closer value. Generally, more data points you have, better the experimental result. So you can do, instead of 1 volt, you can do half a volt increments. So then you get like 20 data points. But this should be enough. So let's say here, if you take enough, let's say 10 data points, you should get a value that is much closer to the actual measurement, actual value of the resistance. All right, so then you go and answer, is this resistor ohmic? And pretty much then, what is the relationship? What type of graph do you get? Can you then say that this graph or this resistor obeys Ohm's law, and all of those things? And then you look at then the second experiment, which is here's basically, you take the data for the second experiment, you come back to the video, change it to the electric motor, for example, and then repeat this exactly same steps. So you can see, right? Once you start turning the voltage, then see how the current changes, and then make a measurements, voltage versus current, and then see what you get. Is this ohmic or not? And hey, look at the graph, look at the type of shape you get, and the resistance value, and all of those things. All right, so obviously then you have the light bulb. So same idea, right? You can see it's exactly same connection. Here the light bulb acting as a resistor. Then you look at in terms of how the voltage changes with, as a function of time. Same with, I mean, voltage, we're changing, right? So voltage is changes, current is changes, and you can see also the brightness. Brightness is pretty much proportional to the current. More current, brighter the light bulb. Again, take the measurements of voltage, current, plot it, and see how those things are related. All right, should be relatively straightforward. Um, so you can see, right, there's, trial 3, trial 4, and then here analysis, where you just pretty much summarize your experiment or experiments, right, and talk about, your result. All right, so if you have any question, feel free to email me.